Well, here we go again, the final exam review, part 5. We're going to continue with what we were doing in the previous one, which was looking at the two-sample problem. We started talking about the test statistic, and here what we're going to do as far as finding the degrees of freedom, we're going to use the conservative method, and we'll use this on our final, where you take the smaller of n1 minus 1 and n2 minus 1. So you just look at which sample has the smallest size, and from that sample, that's how you're going to determine what the degrees of freedom are. So looking at how we build a confidence interval, and one thing that I missed is that we will give you the quantity in the denominator, the standard error of the two means independent, just because it takes a while to calculate that. So on the final, we'll give you that value. So when you are doing the confidence interval, all you need to do is find the critical value, multiply it by the standard error we're going to give you, and then you add and subtract that from the difference of those two means. Now let's look at Chapter 20 problem when we worked with proportions. Now again, we have P1 equal P2. That's if we always assume that the proportions are equal. And then either we're going to think that one proportion is greater than the other, or proportion 1 is less than proportion 2, or that they're just not equal. Now, when you do your test statistic, it will look like your sample proportion for sample 1 minus your sample proportion for sample 2. You subtract those two, and in the bottom, we have what we call this pooled proportion when finding the standard error. Remember what the pooled proportion is. P hat is x1 plus x2 divided by n1 plus n2. So we put that value, we literally take the two samples as if they're one, we pull them together, and that's how we do our standard error. Well, you will have to calculate the pooled proportion. That's something you're going to have to do. But we will give you the standard error when calculating the test statistic, because that takes a little bit of time to do that. So again, you are going to have to calculate this pooled proportion, P hat, which equals your number of successes in sample 1 plus the number of successes in sample 2. You divide that by your sample size for sample 1 plus your sample size for sample 2, and that's what we call the pooled proportion. You will be asked to do that. But when you're calculating the test statistic, even though we'll have you calculate the pooled proportion, we still will give you that standard error, the denominator in our Z0, so that you don't have to do all that work. And once you have that, you also, we can also make confidence intervals, and again, we'll give you the standard error. All you have to do is find the critical value, but we already know this for the common confidence intervals. And so all you do is you take P1 hat minus P2 hat, add and subtract the product of our critical value times that standard error. Now, we showed you what you'd have to do and what your test statistic looked like and how to do the confidence intervals, but when do you know you can do them? There's this fabulous flow chart that Dr. Davis made to look at. So we're going to look at the population mean. If our population distribution is normal, that's the question. If your answer is no, then you have to look if your sample size is greater than or equal to 30. Again, if the answer is no, are you given a sample? Like, in other words, do you have the data? If your answer is no, then you can't do T or Z procedure. However, if your answer had been yes to given the sample, well, then you could do the probability plots and the box plots. And if the probability plot looks good and there are no outliers, you could say yes to both of those, then you can use the T and Z procedures. However, if there's some deviation from normality, some major deviation from normality, or your box plots show that you have outliers, then you cannot use the T or the Z procedure. Now, back to n being greater than or equal to 30. Had you have said yes to that, then the central limit theorem can be evoked, and your sampling distribution of the sample mean can be considered approximately normal, and therefore you can use the T and the Z procedures. Now, going all the way back, if the population distribution is normal, you had answered yes to that, then there you go. You have to do you definitely can do the Z and the T procedures. So the sampling distribution of the sample means, no matter what the sample size is, would be considered approximately normal. Now let's look at the difference in two population means. Now this is when we have the independent case. So let's look. Both population distributions are normal. If you answer no, then you have to see if both samples are greater than or equal to 30. If your answer to that is no, then are you given the data to look at? Are you given the samples? If the answer is no to that, then you can't do the T procedure. However, if we back up and you answer yes to that, then you have to do probability plots and box plots for both the samples, and both of the samples have to have no major deviations from normality and no outliers for us to be able to use the T procedure. If either one of them has any deviations or has an outlier, then you cannot use the T procedure. So it has to be an and here. Both have to show no major signs of deviation from normality and no outliers. So let's go back up one more. If both sample sizes were greater than or equal to 30, well then by the central limit theorem, we could have said our sampling distribution of the differences in the means is approximately normal, and we could use the T procedure. And if we backed up even one more, if both distributions were normal, both populations were normal, and we knew that, then we automatically would have been able to do the T procedures. So again, we have to assume that the two independent samples were taken from simple random sample, treat the inference for matched pairs, dependent samples, as a one-sample problem using differences. We talked about in the last slide. So make sure that when you use this flow chart that you see here that we have an independent case. Otherwise, the dependent case, you go back and you treat the differences, and then it's just like a one-sample t-test. Now this is the assumptions for population proportion, strictly as the book had said. I said if you just did n times p times 1 minus p being greater than or equal to 10 all around, that will give you enough so that you would know that you could assume normality. So it was a little more conservative what I gave you. But if you went by these guidelines, you'd be fine. So if we have the sampling distribution of the sample proportion, if the number of successes and the number of failures are greater than or equal to 10, that's what that n times p is. That's just the number of successes, and n times 1 minus p is the number of failures. If they're greater than or equal to 10, and your answer is yes, then the sampling distribution is approximately normal. If your answer is no to that, then you cannot say that it's normally distributed. Now remember, all of our inferential statistics is based on these sampling distributions and them being normal. So let's look at what happened for our significance test. If my n times p naught and my n times 1 minus p naught are both greater than or equal to 10, then I can do the test statistic and it's approximately normally distributed. If my answer is no to that, the large sample test cannot be done. To doing confidence interval, then again, we can just do if our successes and failures are both greater than or equal to 15, then, and we can say yes to that, you can use the large sample confidence interval. And you can even use the +4 confidence interval, it won't hurt. Now, if my number of successes and my number of failures is not greater than or equal to 15, I answer no to that, then as long as my sample size is greater than or equal to 10 and my confidence level that I'm using is a 90% confidence interval or higher, I can use what's called the +4 method. But I cannot use the large sample method. I have to use the +4 method. Now, if this condition isn't met, if my sample size is not greater than or equal to 10 and my confidence level is greater than or equal to 90% confidence, then I cannot use either the large sample or the +4. And again, with these, so let's look at the difference in two proportions, the sampling distribution of differences in sample proportions. If my number of successes and failures for both of my samples are greater than or equal to 10, and I answered yes to that, then I can say that my sampling distribution is approximately normal. Otherwise, I cannot say that. And if I want to do a significance test, then I need to make sure that my number of successes and my number of failures is greater than or equal to 5 for both of my samples. If I answer yes to that, then I can test the statistic, and it's approximately normally distributed, and I can work with that. Looking at the confidence interval, if my number of successes and number of failures are both greater than or equal to 10, and I answer yes to that, I can do the large sample confidence interval or the +4 method. If I answer no to that, then as long as my sample sizes are greater than 5, I can use the +4 confidence interval.